Well, good afternoon, everybody. My name is Mike Lawton, and I appreciate I'm the guy keeping you your coffee and some fresh air. So I intend to keep this fairly fast-moving and live. I'm presenting on behalf of my colleague, Dr. Yoshiro Ogi, who unfortunately can't be with us today. And in fact, Yoshiro was finishing his slides early this morning. So the content and order of this presentation will be as much a surprise to me as it is to you. So let's see how we get on. It was introduced as a VHF antenna. That's the second presentation from Oxford Space Systems this afternoon, which I also have the pleasure of giving on behalf of another colleague in a similar situation. So this is about an X-band deployable ribbed antenna, and it's interesting that a couple of presentations this morning made reference to deployable parabolic antennas. So I'll show you exactly what we've been doing in that area. But before I start, maybe a bit of gratuitous market research. Who's actually heard of Oxford Space Systems? Kind of put your hand up. That's not too bad. Well, by the end of today, you can all that. So let me give you the quick background. Here's the short CV of the business. I founded the company in 2013, back into 2013, but only really got going when I secured some significant venture capital investment in 2014. So I'll save you doing the maths. We're coming into our 5th year of life. And what we're doing is developing a new generation of deployable structures. And this is antennas, boom systems, and panel arrays. But what we're doing differently, and the reason we managed to raise the level of VC investment we have done, is our approach is a lot different. We're very commercially focused, and we use proprietary materials that we're developing ourselves. And I've got an example here today. So you're obviously very familiar with carbon fiber. For those of you with fishing rods and tennis rackets, maybe if you're rich enough, a car, you could actually prepare carbon fiber. Normally a thick, rigid material, not normally very flexible. So part of our intellectual property is playing around with the formulation of that material to make it do interesting things. So here's a carbon fiber roll. We can make it into a self-deploying structure. Now, deployable carbon fibers aren't new, but the IP we've developed is making this robust enough for the space environment and being able to predict its behavior when you subject it to things like atomic oxygen radiation. So this is a simple material. This is the simplest thing you could ever make. I'll show you how we turn this into a product in the following slide deck. I can use it by throwing it around as well. So we develop a lot of intellectual property. We apply for 5 formal patents. This is the stuff that investors get excited about, how much intellectual property collateral you have in the business. But I get more excited through IP that I call protection by complexity. So I can show you this material. It doesn't mean you can instantly go away and replicate my intellectual property. It's a bit like the code formula. So that IP is actually a lot more valuable than things we can put into patents. My team is now 28 full-timers. I'm recruiting. So if there's any really smart thermomechanical engineers out there, or RF engineers, then please come and see me. We actually have contracts with most of the European primes, as well as satellite builders in the US, as well as Asia. So we've got some great commercial action. And we find ourselves the showcase so-called NewSpace company for Innovate UK, which is the UK government's innovation agency. And anytime there's overseas promotional activity for the UK, invariably OSS gets dusted off. And this graphic is aspirational, but it will be reality next month. This is our new headquarters that we're building in the UK to accommodate our commercial expansion. I'll show you exactly where we are in the UK. We're about an hour outside London on the largest science and research campus in the UK. About 6,500 people now on campus. 80 space companies are actually there, employing over 800 people. And the government recently announced a €100 million expansion of RAL Space. So some colleagues from RAL Space are in the audience, so congratulations on a £100 million expansion to your facility. And that's actually putting in place more thermal vacuum chambers, environmental test facilities that commercial companies and academia can come and use. Okay, on to what I want to talk to you today about. So this is a live development we're currently doing for a US customer. So for reasons of confidentiality, I can't name the customer, and I've had to redact some of the material, or I hope the show has redacted some of the material, but we'll find out. So it's about developing a deployable parabolic antenna. Ultimately, the customer wants a 5-meter unfurled antenna that will fit, ideally, on a 27U spacecraft. That's the challenge they've set us. they're willing to go with a 2.7 meter diameter for their first IOD. So we're under contract to demonstrate our capabilities to give them a 2.7 meter antenna. So the idea is we're under contract to produce this first TRL3 breadboard. So the top level requirements actually set us is, they're calling it a disk format. It looks like a sort of large donut on stone. This is the target. They want it to sit on top of a 27 craft. Mass, as ever, is the general concern, so no motorized deployment, don't have the mass for it. So they want it to ride and store there. And of course, it has to be thermoelastically stable materials to survive the space environment. So here's a very simple CAD image of the target that they've set us. And of course, being a commercial project, it could cost nothing and be ready next month. That would also be desirable. So very, very aggressive commercial timelines. To give you an idea of how fast we have to move, if they like what we're doing on this breadboard, they will want flight hardware from us within 14 months. Otherwise, we won't get the contract. That's how aggressive the US colleagues can be. Okay, I won't labour all the way down through the specification. It's partly a focus as well. But the top lines are: it's a 2.7 meter architecture operating at X-band. So you can probably guess the application. And the translates into the technical challenge of RMS surface accuracy, just how precise this parabolic needs to be when it's deployed. If you crunch the numbers for this typical mission, it comes out around that wavelength of lambda over 50 to lambda over 100, which translates into 0.3 millimeters of RMS surface accuracy across the entire parabolic, which is a pretty tough challenge for the deploying structure. It's a Cassegrain configuration, which means we need a primary reflector and then a secondary reflector product. Of course, the other thing is, as ever with CubeSats, the stowage volume is also an internal concern. Okay, so even these types of antennas aren't new. So here's something from the history books, probably before much of the audience was actually born. From 1970, Lockheed Martin played around with what we call wrapped rib antennas. So the one on the left is a 10-meter structure. And the colour image in the bottom right-hand corner. Anybody want to guess how big that one is? Those aren't photoshopped people; they are actually there. It's 25 meters in diameter. So why are they using such large antennas? Well, Lockheed Martin come from the US Department of Defense background. Therefore, officially, no one knows what they're doing with these. But it's Earth observation and eavesdropping from all that. But of course, if you come from a US DoD background, cost is not your concern. So they don't really care how much these things cost, as long as they work. Our challenge is a very cost-effective architecture that's compatible with CubeSat budgets and Microsat budgets. So it's more recent work. This is done by Sergio Pellegrino, one of the sort of gods of deployable structures in carbon fibre, now working at Caltech. And his PhD student, also now a professor, is Professor Zong Yu. He is Professor of Structural Engineering at Oxford University, which is about 10 minutes drive away from me. So Professor Zong Yu has now become one of my closest collaborators. So we're getting a lot of origami design expertise into our team as well. So it's combining that knowledge of how you fold structures in a really model way without creasing the surface is something we're now using. So we're actually building on a lot of work done by you and So the technical challenge, as I mentioned, it's all about stowage volume. That's especially high constraint in this particular application. I talked about the reflector backing structure being a big challenge. Ultimately, they want 5 meters. We're doing 2.7. And the reflector materials themselves, we want them strong enough, stiff enough to give us a reliable reflector surface, but we want them to stow as well without damage and survive. In this particular operation, it's X-band. Ultimately, we want this architecture to work up to Ka band, and that's a development we actually started in the summer with some support from the NewSpace agency. I mentioned it's a Cassegrain antenna, which means we need a sub-reflector. And we set ourselves the challenge that, once again, we can't have motorized deployment for this secondary reflector. So, like the primary reflector, it has to be passively deployed using stored energy. Of course, if you're deploying something into the field of view of your primary reflector, the last thing you want it to do is impinge on the RF performance. So we want this to be RF transparent if we can. So here is our early architecture. This is going back to 2015. This is when we first started talking to this US customer. You can see how we were evolving our thinking. You can see when it's deployed, we have some Kevlar cords, tension cables coming down. We actually discounted that, saying it was too complicated and was adding too much cost to the design. So actually what I'm going to show you now is a refinement that we're currently working towards. You can see the size of the craft, roughly 500 millimeters by 500. Ideally, they want to get that a little bit smaller, as I said, approaching 27 years from now. So, taking our composite expertise, we designed and developed a very low-cost lenticular rib. And the screen's not fantastically bright, but I've got a little section here, probably the world's shortest lenticular rib. See the construction and hopefully the shape. And this will stow and bend as well. A lot of bending is very small, but you get the principle. So it's actually two sections of carbon fibre together, welded, overcoming separation to lamination is one of the challenges that we've established on the project. These structures actually contain a lot of energy, so the challenge is how we wrap these carefully and repeatedly without damaging them, but also in such a way that when we release them, a controlled release of energy. So a lot of time and effort spent doing this internally to do something like that work. So that's the primary structure. We talked about the secondary reflector, so Cassegrain top lid. We talked about passive deployment means. So once again, here's a variation of our flex composites that have a compressible, stowable tower. So very, very tunable material. We can actually get a surprising amount of energy in this tower, such that when we release it, it wants to pop up. And I can't tell you the exact formulation of the material because we did manage to crack the problem of making this not quite RF transparent, but surprisingly compliant to this particular application. We have a patent in progress for this particular design. As ever, it's not just a mechanical structure, of course, it's an RF structure. So I have some pretty heavyweight RF expertise on the team, so we did a huge amount of RF analysis, convincing ourselves this was actually going to behave as an antenna. You'll be pleased to know I'm not an RF expert at all, so I'm not going to attempt to explain all these fancy parts. I'm sure there's an RF expert in the audience. I've been told this is a pretty good set of results. With a maximum gain coming pretty much close to what you can expect theoretically from this type of configuration. No one is shouting out, so I'm assuming there's no RF expert. Okay, so coming closer to what we actually ended up building, you can see here we are, 270 or 2,700 millimeters, 2.7 meters when fully deployed, 910 millimeters from base plates to top of the secondary reflector. And now just introducing in the photograph on the right hand side the surface material. So we looked around, could we make a flexible carbon fiber skin? We do actually have one of those on a separate development. But we actually started development of our own proprietary metal mesh. So for those of you that haven't seen antenna metal mesh, it actually looks looking like a lot like ladies' tights, believe it or not. So it's pretty indestructible. I think it's probably secondary industry making indestructible ladies wear. So the idea is we use wires that are thinner than a human hair diameter. That's a proprietary knitting pattern, but it allows, when we tension it, to actually remove all the surface greasing. So I can crush this up pretty damn tight, then when I stretch it, I actually remove all deformation in the surface. You can probably see some little features for those of you in the front row. This is a very low-cost way of attaching to the vacuum structure that we also have a patent. I won't tell you the exact material that we use for flights. This is an internal development funded by the So that's the surface. Here we are building the thing. If you do close-up pictures, then it looks really big, but still 2.7 meters. We worked out a really low-cost way, actually, of avoiding expensive HDRMs. And in the top right-hand photograph, you can see what I call the large white solid bulb. That's actually the secondary reflector. And you can see those little slots in that structure. The ribs, when stowed, actually interface to those points. such that it essentially clicks down into place. And then when we release that central mass, it pops the secondary reflector out of the way, allowing the ribs to come out. So it's a very low mass, very simple way of achieving a very reliable system. But what's coming next? So to prove that we can achieve the RMS surface accuracy the customer is looking for, a lot of people historically put little laser targets, little optical targets on discrete points on the surface of the dish. But that doesn't actually give you the full surface profile. So we invested in a handheld, non-contact laser scanner. You can probably just see the guy hanging off a gantry in the picture. What he's doing is scanning a wand over the surface of the antenna. And actually each pass of that wand generates 10 million data points. So it actually takes 2 or 3 days to complete surface scan to give us what you see in that computer image on the side. And that means we can then take what we've measured in the real world and then map it back to the predictions made analytically, so we can switch on and switch off gravity to verify we're actually getting what we expect to see. I'll just end, actually, just in time, with a deployment video. So here's the first ever deployment of the breadboard. I'll let you see it first, and I'll talk you through what we're looking at. So this is completely undamped. You can see the central mass is wobbling all over the place. That's not optimized yet. But because it actually worked the first time we tried it, we thought it was a pretty neat video, so we're sharing this for the first time in public. Here it is in slow motion. So we've done a number of stowage and deployment cycles to verify surface accuracy. And we're actually exceeding the results we're looking for. So we're very pleased with this. This is very scalable. We can go down anywhere to around about 50 centimeters and then up to 5 meters. As I've run out of time, thank you for your attention, and I'm happy to take any questions. Thank you.
Any questions?
Hi, thank you for the presentation. You already mentioned the center of mass is wobbling all over during deployment. I assume for a primary customer that's not so much of an issue with fully stabilized spacecraft, but for CubeSat missions that might be an issue.
Yeah, what you're looking at is the first deployment of the first ever breadboard. That's now been optimized and it's a much more stable deployment. So for a flight unit, we'd include some kind of damping. So on a microsat, that would be an eddy current damper to tune out that line of release.
And what will do TRL6?
They signed the contract this time next year.
Any further questions?
For the secondary, when it's deployed and stabilized, what would be the accuracy we can achieve in terms of the ideal position?
Yeah, that's a good question. So we can hit the accuracy for X-band operation, which is around about 10 gigahertz operation for this type of antenna. I don't know the exact millimeter precision, but it's compatible with a 10 gig operation.
Any final questions? Yes, thank you again.